everyone. I welcome you all to today's webinar. Our guest speaker is Dr. Rajiv Gupta from IIT Goa. He is working as an assistant professor in IIT Goa. He has 9 years of teaching experience across many well-known universities. He has secured his 18th rank in NET examination in 2011. He has 9 international and national publications in journals in his credit. He has been awarded as Inspire Faculty in 2018. I welcome you, Dr. Rajiv Gupta, for his talk on von Neumann inequality.
You just give me 1 minute. Yeah, just 1 minute. I will just tell him to call. हाँ विमान जी, मैं 1 घंटे बाद कॉल करूँ? Okay. Thanks Ethel, thanks for the introduction, and and thanks for inviting and giving this opportunity to interact with all of you people. And just there is a minor correction in the introduction, and the correction is I don't have 9 years experience of teaching. Yeah, I have been TAs in many courses, but as far as proper teaching is concerned, I have only 1.5 years or maybe approximately 2 years of experience. Okay, but anyway, so let's start with the lecture. We will okay, let me just because it is not useful, so okay. So as you can see, I will be talking about von Neumann inequality and basically von Neumann inequality. Other things will come into in the path. So what is it? What kind of inequality it is? So for that, I just need to first set things up. So in this lecture, what we are going to do is we'll be considering polynomials, and whenever we are writing P, it means a polynomial initially in one variable in complex plane, and later on we will go to higher variables. But let me first say it is a polynomial in one complex variable. Okay. And second thing which we will consider is a matrix. Okay. So basically a matrix of some size. We will always consider a square matrix. So matrix of size, let's say k by k. So it's a square matrix of size k. A polynomial is can be written as something like this, right? Let's say degree n polynomial, and to say that it's a complex variable. In other words, we would say that these edges are coming from the complex plane. So it's complex coefficiented. Okay. So degree is n, and now what we can do, instead of writing this z, we can talk about something like P of t. Okay, so this is third creature of this lecture, P of t, but this is made out of P and T. How are we making it? It's simple. Instead of z, you plug t. Okay. So let me write second term also. Why does it make sense? It makes sense because if you are taking a square matrix, T is a square matrix, then T square is again going to be a square matrix. You can talk about T square, right? and you will again get a square matrix of size K. And similarly here. So all of these are square matrices except this one. Okay. And you can add them up and you will finally get a square matrix of size K. So this one is not so correct. If we are plugging T inside this polynomial, what we need to do is we need to put an identity here. So this identity means identity matrix of size K. Okay. I hope this makes sense now, because it is finally going to be a K by K matrix. Okay, because you can talk about the product. Okay, so these three things are there. Now these are all algebraic, but there are going to be some analysis also. So let me just introduce terms which will bring analysis into picture. So for this polynomial, we'll talk about something like this quantity, norm of P. Let me denote it by d comma infinity. What does it mean? It has a simple meaning. What you do, you try to find out this supremum. Okay. So you can calculate modulus of pz for every z in the unit disk. So if you look at this particular set, mod z less than equal to 1, it is the following. So that is actually in R2, this is center 0 and radius 1. Okay. Mod z less than or equal to 1 means this shaded region. If you look at the polynomial actually makes sense in whole complex plane, but we are only interested in this particular set, and we are computing the maximum of modulus pz over this compact set. Okay, so this is going to be a quantity. Now second thing is related to T. We will also talk about norm T. Okay, this you might have seen, but let me just repeat it. Norm T, and let's denote it by O. So we usually call it operator norm, but this is going to be the following quantity. I will explain it in a while, but just allow me to write it down. And let me put 2 here. What is this creature? So whenever you have a matrix of size K by K, you can treat it as a linear map, right? Right now, we are in the field of complex plane. So it's a linear map from Cn to Cn or Ck to Ck. So because it's a K by K matrix. Now on Ck, there is a very well-known norm, and that is Euclidean norm, right? I will say it. What is the Euclidean norm? So there is a very well-known norm, Euclidean norm. So how is it defined? So if you are taking a vector from Ck, this norm is basically, as you know, it is this quantity. Okay. So now this norm is defined. So what you do, you look at all those vectors from Ck whose norm are less than or equal to 1, and then try to see the image of that vector under T, under the linear map T, and you compute the norm of the output. You do it for every vector with norm x less than or equal to 1, and then you see what is the supremum that we will call operator norm. pictorially, let me just show you so that there is some intuition built. So if you have some CK, okay, so let's say this is your CK and Euclidean norm, this set is also again going to be a ball kind of thing, okay. And your T is actually acting from CK to CK, but in particular it can act on this closed ball and it will map it to somewhere. We know that under a linear map 0 will go to 0, so it will be around this point only. So it could be anything, something like this. Okay, so just look at the image of this unit ball under T. It is some set like this. And then what is exactly the norm? You compute the maximum distance. So right now, I think the maximum distance will be this in this picture. So this is basically the norm T. Okay, so look at the unit ball image and see what is the farthest point. Okay, so this is norm T. And since, okay, by the way, whenever you have some confusion or some question to ask, please interrupt me and shoot the question. Okay. Okay. So we are defining it for T only, but as you can see, it is for any matrix, right? I mean, our T, if you like, our T was an arbitrary K by K matrix. So this definition is not only for T, but it is also for PT, because PT is also a K by K matrix. So it is some S, right? So you can talk about operator norm of S also. That will be supremum of norm of Sx such that norm X is less than or equal to 1. Okay, so this is the setup. Once again, polynomial matrix, plug the matrix into the polynomial because it can be done. And then you talk about two quantities. Now the question is the following. Basically, how are these quantities related? Okay. So these quantities, how are they related? Question can be informally how to compare these quantities, but let me just write formally. If norm T is less than or equal to 1, operator norm, is it true that norm PT operator norm is less than or equal to, I mean, can it be compared with the norm P? Actually, the answer for this question is yes, but let's first look at some specific case, because why somebody asked this question? Why to ask this question, right? So let me just first say why to ask this question. So first point, suppose your polynomial was a constant polynomial. There is no z involved. Then what will happen? If you look at P of t, as there was no z, so there will not be any t in this. So it will simply be a0 times identity. And now if you look at the norm of pt, which is going to be the norm of a0 times identity, but identity norm is 1, so it will be exactly modulus of a0. Okay, and this is exactly norm p d comma infinity. Why? Let's see this. If you now look at norm p d comma infinity, it is by definition is modulus pz mod z less than or equal to 1, and we know what is pz, so This is simply modulus A0. The thing which you are supremizing is independent of Z. So basically there is no supremizing question. It is basically modulus A0. Okay, there is nothing to supremize. Okay. So in this case, it is not only less than or equal to, but it is equal to norm P. Now let's look at first non-trivial case when your polynomial is a linear polynomial. It looks like a first non-trivial case, but this will also be a trivial case. Let's see. So what will be PT? PT will be A0 identity plus A1T. And if you look at norm of PT, so now I'm not writing operator norm here, but it's clear, right? Because the thing involved in this computation is the matrix case, so it is operator norms. Okay, let's write for a while. Later on, we will drop this. And now if you apply triangular inequality, so let me just say it will be less than or equal to, okay. But norm T, we are starting with less than or equal to 1, so it will be less than or equal to mod A0 plus mod A. And this is exactly norm P d comma infinity. This is an interesting computation, so let's see this. I mean, easy but interesting. So once again, we are interested in this particular quantity. And if you just simply plug this, there is a way to, first of all, I think it is clear that it is going to be less than or equal to mod A0 plus mod A1, because here you can apply triangular inequality and your mod Z is less than or equal to 1. So by the same reason as you saw here, it is going to be less than or equal to mod A0 plus mod A1. So less than or equal to is easy to see, but why it is equal to? For equality, we just need to find a Z such that it becomes equal to this, right? A Z such that mod Z is less than or equal to 1 and the quantity becomes equal to this. That's also easy. How do you do that? So I want to find a Z such that it becomes equal to this. What I will do, I will choose Z to be some e raised to I theta, and I will tell you what is e raised to I theta. So maybe let me do this. Let's write it something like this. Let me write it to be e raised to I theta 1, because any complex number can be written as r times e raised to I theta, right? So A0 is a complex number. I'm writing it as modulus of A0 times e raised to I theta 1, where theta 1 is basically the argument of A0. Similarly, I can write A1 to be mod A1 e raised to I theta 2, right? And this is your Z. Now, let's take e raised to I theta common from this. I mean, let's take outside. So what happens? It becomes mod A0, mod A1, and then it is e raised to I theta 2 minus theta 1, Z. Now, okay, my aim was to choose a Z such that finally it becomes mod A0 plus mod A1. So what should be the natural choice? The natural choice should be choose a Z such that this thing disappear, right? So choose Z equal to e raised to I minus of this. So e raised to I theta 1 minus theta 2, right? If you do that, if you choose e raised to I theta 1 minus theta 2, so what will happen? It will e raised to I theta 2 minus theta 1 multiplied by e raised to I theta 1 minus theta 2 is 1, because they are conjugate to each other. Okay, so for that reason, it is not only less than or equal to, but it is actually equal to. So if you want to make an intuition about this computation, the intuition is the following. If you are supremizing only two terms and you have a freedom here of choosing any argument, then what you can do, you can choose an argument of z such that it kills the argument of a1 as well as of a0. Okay, because there are only two terms, so that's why you could do it. You cannot do it for three terms. Okay, so in this case, we get less than or equal to. Okay, for linear polynomials also we'll get less than or equal to, and that's why this question is there. Is it always true? Is it always true that it is less than or equal to norm p d comma infinity for every what? For every polynomial and for every t satisfying this. Satisfying this. Okay, I hope till now things are okay. Is there anything you would want to say? Yeah, these things are, yeah, okay. They turns out to be trivial or not so non-trivial either. So actually the first non-trivial case is when p is a polynomial of degree 2. Okay, but before going to specializing ourselves to degree 2, let me first prove this. Let me first answer this question in general. And that is exactly von Neumann inequality. Okay, so norm p is less than or equal to 1. Let me try to indicate the proof. Proof is simple, so I will just try to indicate it. Here we will use one result from, actually two results from linear algebra and a result from complex analysis. So maybe first let me say what is the result we are going to use. If T is a matrix, we can decompose T into a unitary and a positive matrix, right? This is called polar decomposition. This is called polar decomposition. It's like, why it is called polar decomposition? Because it's like complex plane decomposition. In the complex plane, any number z can be written as mod z times e raised to I theta. So e raised to I theta is the unitary part and mod z is basically the positive part. So it's completely analogous to that decomposition of complex numbers. So that's why it is called polar decomposition. So you have a unitary and a positive matrix R. Now second result is, whenever you have a positive matrix over the complex field, then you can diagonalize this using unitary. So basically R can be written as some V star or V star dV, where V is again a unitary. So V star is basically V inverse and D is a diagonal operator. And what you get at the diagonal of D, it's basically the eigenvalues of R. Okay, these eigenvalues of R is exactly the singular values of T. Okay. So finally, your T is something like this. Okay, where D is diagonal consisting of singular values of T. Okay. Okay. By the way, one more result from linear algebra. The result is if norm of T is less than or equal to 1, then the singular values will also be less than or equal to 1. Okay. How should I say this? So let's write down D to be something like this. So K, right? Singular, you call it singular values of T, or you may call it eigenvalues for R. Both are same. Okay. Let me just say, note that lambda 1 and this lambda k, they belong to this. Okay. Because norm T is less than or equal to 1. So it cannot go beyond 1. Now at this stage, what we will do, we will leave this T and we will try to generalize this T. What we will do, we will make these lambda 1, lambda 2, lambda k arbitrary. And we fix this U and V. Okay, the idea is the following. Let me tell you the idea. Idea will be the following. What will be the idea? Idea will be, we know we are interested in this. Okay, for every T, but what we will do, we'll show that this norm PT for our chosen T is less than or equal to norm P of something, maybe T tilde, where T tilde is something good. And good in the sense, it's better than T in the sense that it will be easier to compute this. Okay. And then we will prove that it is less than or equal to norm P. Okay. So let's do that. So this is like idea of the okay. Okay, this is the idea. How to do this. Now, if you look at P of this thing, this is again a K by K matrix. depending on Z1, Z2, Zk. Okay, this is where I will skip some details because it might be boring for you, but let me just say, how should I say this? Let's do one thing. Let's fix Z2, Zk and just vary Z1. Let's fix this. Okay, fix this and just vary Z1. That means you just consider Z1 to be the variable. Others, you choose anything but fix it. You don't vary them. Then it becomes a thing in one variable only, right? It becomes a thing in only one variable. And after fixing this Z2 up to Zk, and if you just vary Z1, you will see that this whole thing will give you a polynomial in one variable. Okay, not right away. Okay, the idea is it will give you a polynomial in one variable, and then you apply the maximum modulus principle for the complex from the complex analysis. Okay, so can I be vague a bit here? I mean, because if I'm going to say things, I think it's already. Let me be vague here. So fix this and apply maximum modulus principle here. What does it say? So whatever this quantity is, after doing something, this is going to be a polynomial in one variable, and that variable that is Z1, you know that it is less than or equal to 1. I mean in modulus. Okay, so you are again in the scenario that your Z1 is coming from here. Okay, center 0, radius 1. So maximum modulus principle says that the supremum, so we will be talking about norm of this, the supremum will be attained on the boundary. Boundary is circle, so let me introduce another notation. So in other words, the maximum will be attained for mod Z1 equal to 1. Okay. Now, once you are done with that, we can fix then Z1 on the circle, and then we can vary Z2, fixing others also. Then we will see that mod Z2 also has to be equal to 1 for the maximum to achieve. So in other words, if we are talking about, if we are solving the following, mod Zj less than or equal to 1 for all this, then it is nothing but mod Zj equal to 1. So that's basically maximum modulus principle. Okay. But as soon as mod Zj is 1, these matrices becomes special, right? So let me just once again write. it becomes a unitary operator. Okay, because eigenvalues are eigenvalues are in the circle, and if you write down the inverse, it is basically the star. I mean, the inverse of z on circle. If z is on the circle, that means if mod z is equal to 1, and then if you are talking about z inverse, that means 1 by z, it is basically z bar, right? Because z into z bar is 1, and therefore z bar is 1 by z. So inverse basically becomes the star or the conjugate. That's why it becomes a unitary operator, unitary matrix. Okay. Now this is a better matrix, right? Better than the previous one. Okay. So since this is a unitary matrix, now let's look at this. It was what? U V star, and then Z1 up to Zk, 0, 0, and V. This is a unitary matrix. All of them are unitary. U is unitary, V star is unitary. Now Z1, this diagonal is also unitary, V is also unitary, and product of unitary will again be unitary. So finally, this is a unitary matrix. And now we will forget about everything. I mean, all this recipe. We have got what we wanted, right? We wanted to just look at this red part. We wanted to show that if you are computing norm PT, you don't need to. Once you can come up with a better T tilde, for which the norm becomes something better, something bigger, and then you actually compare that with norm P, and automatically norm PT will be compared. And that's what we have done here. We have got that if you are working with a T, you can replace it by a unitary matrix. And let's call this to be T tilde. Okay. And as soon as you have a unitary matrix, if to start with, if T was a unitary matrix, then that was a very simple case, because as soon as T is a unitary matrix, you can diagonalize it using a unitary. So something like x star and then some diagonal, and then x, where x is unitary. And why it is simple? Because if you look at PT, it is something like A0 identity. Let me write it in general. A0 identity, A1T, but A1T is x star dx, and then AN. Okay, let's look at T square. What will be T square? T square will be x star dx, x star dx. And if you look at this, since x is unitary, it becomes identity. So it is x star d square x. So here it will be x star d raised to nx. And then you can basically take x star out from this side. And x out from this side. Here I'm writing x identity to be x star x. And now if you compute the norm PT, it is going to be exactly, because these are unitary. Okay, once again, I'm not going into the details. This will be this. And so finally, this is a diagonal matrix, because everything involved here is a diagonal. Identity is diagonal, D is diagonal, D square is diagonal, D raised to n is diagonal. And in fact, if you just look at it, it is exactly P of Z1, P of Zk. If your D was Z1 up to Zk. That's okay. This one can see. Because if you look at, if your D is this, if you look at D square, you just try to product, you will get this. So in other, okay, so D raised to K will be this, D raised to M will be this, and so what is happening is, if you are applying a polynomial to D, your polynomial basically appears here, and that's what is happening here. Your polynomial appears here. And now if you look at the norm PT, it is basically the maximum of the diagonal entries. But these ZJs were coming from the unit disk, or they were of modulus equal to 1 actually. So that will be less than or equal to supremum mod Z less than or equal to 1 mod PZ. Because they are only finitely many points, right? I mean, you are choosing only finitely many of them from here. And here you are talking about the full thing. So supremum over a subset is less than the supremum over a bigger set. Okay, I know I have been some, yeah, I was little vague here, but let's just see what is exactly the idea. Idea is using some standard results from linear algebra, like polar decomposition and diagonalizability of positive matrix and unitary matrix. And the main idea was to do this. Okay, to try to replace T by something better, and something better, as you have seen now, is unitary matrix. So you can replace T by a unitary matrix, and unitary is easier to deal with because as soon as you have a unitary matrix, you can diagonalize it using another unitary matrix. In fact, this is true for any normal operator, okay, normal matrix, that you can diagonalize it using unitary. So unitary, certainly you can diagonalize using unitary, some other unitary. And other part was played by just purely by computation, because T square was x star D square x. And so if you look at basically PT, it is the norm is basically the maximum of these quantities, and this Z1, Z2, Zk were few points from the circle, and therefore that maximum should be less than or equal to the maximum over the bigger set. Okay, by the way, yeah, this concludes the proof of the theorem, von Neumann inequality. Yeah, these computations are important from every perspective, polynomial norms and these norms. Okay, as I said, we'll move to higher variables, and let me just tell you what has been done. So whatever we were doing till now was in one variable. So one can ask the same question in two variables, or for that matter, many variables, but let me just write. So by the way, let me just point out that it was in 1951, I think. Yes, it was in 1951. And This was not the original proof. This proof came later on. And now which I am talking about will be in 1963. So P is a polynomial in two variables. Now, since you have two variables, Z1 and Z2, so if you want to plug operators or matrices, you need two matrices. So T1, T2 are two matrices. But you cannot just start with any two matrices, because in polynomials, what happens is, Z1, Z2 is same as Z2, Z1, right? I mean, that identification is there. They are treated as same numbers, right? Z1, Z2 is same as Z2, Z1. So here also you should start with two matrices commuting. And you should start with contractions. Contractions means that their operator norm is less than or equal to 1. And you ask the same question, and let me just directly write down the answer. And that is 1963 by Endo, Japanese mathematician. He proved much more than this, but we will not go into that. Okay. Now you should ask what is this? Okay, this much is this P1 T2 will be clear, because if you are starting with T1 T2 two K by K matrices, and once you plug in T1 T2 in the polynomial P, finally you will get only a single matrix, single K by K matrix. For example, if you plug it here, let's say in Z1 plus Z2, it will be T1 plus T2. So finally it is a single matrix. And if you plug it here, this T1 square plus T2, it is a single matrix. So this quantity we already know how to define. But this you should ask how to define now, because now there are two variables. And I am sure that your simple answer will be to say that it is defined as, previously we were just writing this. Now, since we have two variables, we cannot do that. We'll have to write something like this. And you simply do this, right? So that's a natural definition, natural generalization of the previous definition. And the answer is yes. So Endo proved this, that it is going to be true even in two variables. Okay, that is in 1963, 12 years later. It was open for 12 years. But if you further ask this question in more variables, okay, so if you ask this question in the more than two variables, the answer is no. Let me just write setup is parallel, like P is a polynomial in, let's say, m variables. And now it is in m variables, so there are Z1, Z2, Zm. So you will have to have m operators, m matrices, commuting matrices with norm Tj less than or equal to 1. And then you ask the following question. Where once again, natural definition is okay. So that's the question. The answer is no. No, it's not true. It's not true if you go beyond 2. Okay, it starts failing at 3, and that was this answer came in 1975. It was open till then. Yeah, we are about to reach our time, right?
Excuse me, Rajiv sir, you have 10
Yeah.
minutes left.
Huh?
You have 10 minutes left.
Yeah, thanks. Yeah, I know. Yeah. Okay. Okay, maybe let me share the slides now. So the answer to this question is no, but let's okay, battery is low. Yeah, let me do this. Okay, I will come to this. So answer to that question is no, but what we can do is we can try to, okay, let me just give me 1 more minute. We can try to ask the following. Can we put a constant here depending on m? Okay, so let me just write it here. Okay, 1 is not working. Will 2 work, or will 3 work? Will 4 work? Something will work or not? That's the question. And the answer is not till date. Okay, not even for m equal to 3. So it's an open problem, a long-standing open problem. Yeah, so it's an open problem. What happens to C3? So the way to attack this problem can be in many ways. You can attack this problem, but there are 2 ways. One, you can take special polynomials, right? Or maybe you can fix some size of the matrix. For example, you can fix the size to be 2, and then you can ask whether it is going to be true, fix size to be 3, and so on. But we will follow the first method. We will try to specialize our polynomials. For example, in the previous case, we specialized to a degree 0 polynomial, where the answer is yes. Here also it will be yes. And then you can specialize to degree 1 polynomial, and again the answer will be yes, using the same methods. And then you can apply to degree 2 homogeneous polynomials. Okay, the answer is once again no. So there, let me just show you this. Okay, I want to return down, so 1 more minute. Okay, you can see this, right? I mean, this norm PT, I'm actually kind of comparing it with norm P and norm T both. Previously, I was considering only norm T less than or equal to 1, and then I was asking whether norm PT is less than or equal to norm P or not. But to calculate that constant Cm, what I will do, I will consider norm P to be less than or equal to 1 and norm T also to be less than or equal to 1. And then I will simply ask what can be the possibly, how far it can reach, the norm PT, how far it can reach. And let's denote it by Ckn. Why Ckn? Because n is the number of variables in this slide, and k is the degree of the polynomial P. As I said, I will be fixing the degree. I mean, we will try to go slowly, degree 0, degree 1, degree 2, and so on. In this lecture, we will only restrict ourselves to degree 2. So P, for our purpose, P will be of degree 2 homogeneous polynomial. Homogeneous we can actually forget, but let's keep homogeneous also. Homogeneous means there is no constant part, there is no linear part in the polynomial. So P is a polynomial of degree 2, which is also homogeneous. Then that particular constant is going to be in between. If first of all, it is going to be less than or equal to 2 times kgc and bigger than or equal to kgc. Now, what the hell is this kgc? KGC is a very interesting quantity, and this can be treated as a this is of independent interest, the quantity KGC. Even if it takes 5 minutes, I will try to explain this, because this is a very important quantity from many point of view, from computer science point of view and many things. So let me just try to explain this quantity. As you can see, I'm starting with a complex array. Okay, so right now I have a n by n complex matrix which satisfies the equation 1, that is summation ajk sj tk is of modulus at most 1 if your sj and tk are coming from unit disk. That is, modulus of sj is less than or equal to 1 and modulus tk is less than or equal to 1. For any fixed complex array, the equation 1 may not be satisfied automatically, right? Because ajks might be very, very big. So we are imposing this condition on complex array. And then what we will do, instead of writing sj and tk, we will, instead of writing sj and tk, let me just, instead of writing okay, this doesn't write. We will choose xj and yk from let's say ck. Ck means they are k tuple. Okay, here sj and tk are single complex numbers. Here xj and yk are k tuples. So you can compute the inner product, and you can ask whether this quantity summation ajk xj inner product yk, which is certainly a bigger quantity than the previous one, summation ajk sj tk, because here you are taking xj and yk from ck, okay, or from cm. So what happens to this quantity? And it turns out that this quantity is going to be less than or equal to some constant k, and this constant k will not depend on the length of the vector xj or yk. Okay, if you want to choose 100 length vector, that also is allowed here. And in fact, this constant k will not depend on the matrix ajk. It doesn't matter what matrix you choose, that k will still be independent of that. And that constant is called kgc. We are denoting it by kgc. It is called complex Grothendieck constant. As the name suggests, you can actually have a real Grothendieck constant also if you are working in the real field. But anyway, so it's a complex Grothendieck constant. And interestingly, this was in 1956. Okay, this result was of Grothendieck, and it was back in 1956 in his PhD thesis. From then, it is still unknown what is exactly the value of this constant. But what is known is that it is in between 1.33 to 1.404. Okay. The value is still unknown. It's one of the biggest problems open. But this constant appears at many places. And interestingly, it appears here also in the work of Varopoulos in 1976. I will not go into the proof. But as I said in the abstract, we will improve these two bounds. If you look at the left-hand bound, it is 1 times kgc. On the right-hand side, it is 2 times kgc. And these two can be improved a lot. And we can improve it to 3 root 3 by 4, which is approximately 1.3. I'm not going into the proof. Proof basically is Schwarz lemma and nothing more than that. Schwarz lemma from complex analysis. And you can improve this lower bound also. Okay, I will have to skip this. But lower bound you can improve up to at least 1.118. So it's certainly bigger than 1. In fact, when Varopoulos did this result in 1976, he was thinking whether this limit is exactly kgc or not, and he was trying to get rid of these two, but he couldn't get rid of these two because of obvious reason, because you cannot. That's what we have shown, that you cannot get rid of 2. At best, you can improve it. Okay, I will stop here. Yeah, thank you.
Thank you, Raju sir, for this knowledgeable and informative talk. Thank you everyone for to be a part of this webinar. Any questions, dear faculties? Any questions? Thank you, Rajiv.
Yeah, welcome, Michael. Thanks. Yeah, sorry, I had to be a little faster than I thought I
Thank you
will.
so much to be a part of Parvin University, guest speaker.
Yeah, okay. Yeah, thanks a lot.
Okay, bye, Rajiv.
Yeah, bye.